Hi students, Professor Nugent here. Let's talk about forecasting stationarity and the mean squared forecast error. Forecasting and estimation of causal effects are quite different objectives. For estimation of causal effects, we were very concerned about omitted variable bias, control variables, and exogeneity of the independent right-hand side regressors. For forecasting, omitted variable bias isn't such a problem. We're not going to worry about interpreting the coefficients in forecasting models. There is no need to estimate causal effects if all you want to do is forecast the value of the left-hand side variable. What is paramount instead is that the model provide a good out-of-sample prediction, an out-of-sample prediction that is as accurate as possible. For the in-sample model to be useful out of sample, and what we're saying is that you have a sample of data and you come up with a model, you come up with coefficients based on a sample of data, that those coefficients give a good prediction based on scenarios that are not contained within your sample of data. So for the in-sample model to be useful out of sample, the out of sample period, which is typically the near future, must be similar to the in-sample data, which is the historical data, and this is a condition called stationarity. And let's think of an example. A very common forecasting exercise is to forecast economic growth, current economic growth or economic growth next quarter. We forecast current economic growth because economic growth data is not simultaneously available, and we forecast economic growth next quarter to help businesses forecast economic growth next quarter to help inform business decisions. And what do they do to forecast this economic growth? They use forecasting models based on economic growth that occurred over the previous, say, 20 or 30 years. And in order to do this well, the data that they use must demonstrate stationarity. So the out of sample, or the growth that they're predicting, must have the same characteristics of the growth that they used to come up with their model. So let's talk about stationarity. A time series yt is stationary if its probability distribution does not change over time. That is, if the joint distribution of ys plus 1, ys plus 2 through ys plus t does not depend on s. Otherwise, yt is said to be non-stationary. A pair of time series xt and yt are said to be jointly stationary if the joint distribution of xs plus 1, ys plus 1, xs plus 2, yx plus 2, all the way through xs plus t and ys plus t does not depend on s. Stationarity requires the future be like the past, at least in a probabilistic sense. Stationarity says that history is relevant. Stationarity is a key requirement for external validity of a forecast made using time series data. For now, we're going to assume that yt, our dependent variable, is stationary, and we're going to return to this later. I want to sort of emphasize that more about stationarity. What this means is that things like variances are constant over time. Okay, that's one of the big implications of stationarity, that we're able to assume that variances are constant over time. And this is going to play an important role. Alright, let's talk about forecasts and forecast errors. A forecast is a prediction of the future based on time series data. Because the forecasting model is estimated using historical data available at the time the model is estimated, a forecast is an out-of-sample prediction of the future. An example of this is predicting what economic growth will be next quarter based on 20 years of data of economic growth to come up with a model. Forecast can either be one step ahead, for example, next month if you're using monthly data, next quarter if you're using quarterly data, or multiple steps ahead, like 4 months from now or 4 quarters from now. Multiple steps ahead, I will caution, multiple steps ahead forecasts are much more challenging, and the accuracy of each step becomes much more difficult. If we let the estimation sample be t equals 1 through uppercase T, the one step ahead forecast is given by y hat t plus 1 given t. And hat means that the forecast of y is based on an estimated model. The forecast of y is at date t plus 1. So we're thinking about next quarter, where this quarter is capital T. The forecast is based on data through date t. So this is assuming that we have data on economic growth through the current quarter. And the forecast error, this is the hypothetical forecast error, is the difference between the true value of y at t plus 1 minus the estimated value, the forecasted value of y t plus 1 based on data through date t. Okay, this is hypothetical because we do not observe y t plus 1. Let's discuss some terminology and notation of forecasts. Predicted values are in sample. This is the usual definition. Forecasts are out of sample. This is typically in the future. This can also be outside of the region. There's a space-time domain, and so if we're working with things like panel data, the forecast could, it doesn't necessarily have to be in the future, but it could be for another region. Let's think about the notation. So we have talked about the forecast of y for t minus 1 given data through t. That's the forecast of y t plus 1 based on yt minus 1, all the way down to 1 using the population true coefficients. Right? This is not an estimate. Y hat t plus 1 given t is the forecast of yt plus 1 based on the data through t using the estimated coefficients, which are estimated using data through period t. A multi-step ahead forecast is for a date more than one period in the future, specifically an age period ahead forecast made using data through date t is denoted y hat t plus h given t, and economists would caution against this. You don't want to forecast too far into the future because it is hard to predict the future. Let's talk about mean squared forecast error. The mean squared forecast error is a measure of the quality of the forecast. Specifically, the mean squared forecast error is the expected value of the square of the forecast error. When the forecast is made for an observation not used to estimate the forecasting model, in other words, an observation in the future, using the square of the error penalizes large forecast error much more heavily than small ones. And this is a key to this statistic. A small error might not matter, but a very large error could call into question the entire forecasting exercise. So mean square forecasting error, again, this is the expected value of the square of the forecast error, where the forecast error is the difference of the true value of y at t plus 1 and the forecasted value of y at t plus 1 given data through t. We will talk about ways to actually estimate mean square forecast error because we need some way to get at yt plus 1 because up until now yt plus 1 is unobserved, so mean square forecast error up until now is unobserved. We will talk about a few methods shortly as to how to estimate mean square forecast error.